Alright, so this video is going to be part 6 of our sequences and series review. Okay, this video will be the second of 3 videos regarding our series tests. Okay, the series, if our series are going to converge or diverge. So right now we're on the comparison test. We've done the test for divergence and the integral test. So now we're on the comparison test. Now what we want to do is compare, if we had some series, the sum from n equals 1 to infinity of a sub n. Okay, we want to compare this a sub n to some other b sub n. Okay, and this is for something like 1 over n squared plus 1, where it's so close to being a p series, or just something that we know converges or diverges. Okay, and if you compare it to that, and a sub n happens to be less than or equal to b sub n, okay, then and the sum of b sub n converges, okay, well then the series with a sub n will converge as well. Now, if a sub n is greater than or equal to b sub n and b sub n diverges, then a sub n is going to diverge as well. Okay, so that's kind of how it goes. If this doesn't really make sense to you, this concept, definitely go check out my video on comparison test. All right, I dive in. I'm a lot more in depth there. This is kind of just supposed to be a review video. All right, so one thing to note, both a sub n and b sub n must be series with only positive terms. Okay, only have positive terms. So it can't be like 1, -3, 5, -7. Okay, it needs to be 1, 3, 5, 7. Okay, it cannot have any negative terms. Now, let's try utilizing the comparison test here. We have the sum from n equals 1 to infinity of 1 over n squared plus 1. Okay, so our a sub n is 1 over n squared plus 1. And this is so close to being a p series, as I mentioned before. 1 over n squared is a p series with p equal to 2. Okay, and that's something we can easily figure out if it converges or diverges. So let's make our b sub n 1 over n squared. Let's compare it to this 1 over n squared, which, like I said, we know that is going to, if that's going to converge or diverge. In this case, since that p is 2, and which is greater than 1, we know it converges. So anyways, let's see what the relationship is here between 1 over n squared plus 1 and 1 over n squared. So let's write it out like this. 1 over n squared plus 1 and 1 over n squared. Okay, well this n squared plus 1, this denominator is larger than this denominator, okay, while the numerators are staying the same. So you know that this whole fraction is going to be less than this whole fraction. Okay, so you're going to have this sign here. Okay, so this is where a sub n is less than b sub n. Okay, this is our a sub n, this is our b sub n. And does b sub n converge? Well, yeah, it does. So we know that a sub n converges as well. Okay, so since this series converges right here, the sum from n equals 1 to infinity of 1 over n squared, we know that converges. Okay, I figured I'd just write it out for you. So we know that this series is convergent by the comparison test. So now we're going to move on to the limit comparison test. The question here is what if the limit, or if the direct comparison test, okay, that's the one we just did, the direct comparison test, also known as just the comparison test. But anyways, what if that fails? Okay, well, so for this example down here, the sum from n equals 1 to infinity of 1 over n squared minus 1. Okay, if we have that minus 1 there, well, that means that the denominator here is going to be smaller than this denominator, which means that this fraction will be larger. And that doesn't help us because we know that 1 over n squared converges. If it diverges, well, that helps us a lot because then we know that this is going to diverge as well because this is greater than this. But this converges. So the convergence test, or the comparison test, is going to fail. So what we do now, okay, is we now just do the limit as n approaches infinity of a sub n over b sub n. Okay, our b sub n is of course here, our a sub n is here. And if that equals c, where c is greater than 0, so it's positive, and it's finite, so it's not infinity or anything like that, either both series are going to converge or both series are going to diverge. Okay, and that helps us because we know that 1 over n squared converges. Okay, so if we can prove that the limit as n approaches infinity of a sub n over b sub n is equal to that some whatever c, and c is going to be greater than 0 and finite, well, then we know that this series converges by the limit comparison test. So let's see if we can do that. Now we know that our a sub n is equal to 1 over n squared minus 1. And b sub n, that's our compared series, right? B sub n. Now we know that our a sub n is just going to be 1 over n squared minus 1. Okay? That's just our, that's what we got in that summation. Okay, it was 1 over n squared minus 1. Now our b sub n, that's our compared series, right? So that's going to be 1 over n squared. That's what we're comparing to. So we're going to take the limit as n approaches infinity of 1 over n squared minus 1 over 1 over n squared. Okay, that's a sub n over b sub n. Now we can just flip this, so we get the limit as n approaches infinity of n squared over n squared minus 1. And well, we know that that limit is going to be equal to 1, right? Because we have, well, an n squared here, that's the highest power of n on the top, and an n squared here, that's the highest power of n on the bottom. And our coefficients are both 1, so we get a 1 over 1, that's equal to 1. 1 is greater than 0. It's also finite. Okay, so we know that either both series are going to converge or both series are going to diverge. And of course, we know that this series with 1 over n squared is going to converge. So this series is convergent by the limit comparison test. Alright, so lastly we have the alternating series test. Now the alternating series test, we can use this when we have alternating like terms with alternating signs. Okay, so something like -1, 2, -3, 4, -5, right? So you can see that the sign is alternating from negative to positive. Okay, and that's when we want to use the alternating series test. Okay, so I have this little if-then statement. If b sub n, okay, and we'll figure out what b sub n is in a second. If b sub n is decreasing for all n, and the limit as n approaches infinity of b sub n equals 0, then the series is convergent by the alternating series test. Okay, so your a sub n is still your -1 to the n over n. Okay, for this example here. Now your b sub n, okay, your b sub n is just going to be your a sub n, but without what is making this alternating. Okay, what is making the signs alternating? So we're going to take out that -1 to the n, and our b sub n is going to be 1 over n. Okay, and we need to see if this is decreasing for all n, and if the limit as n approaches infinity of this equals 0. So let's do that. Is this decreasing? Well, let's look at the next term in the series. The next term in the series would be 1 over n plus 1, right? You just put an n plus 1 in for n. Now, you know that this denominator is bigger, so this fraction overall is smaller, which means that indeed this is decreasing for all n. Okay, put a little check mark right there. Now, what about the limit? Okay, is the limit as n approaches infinity of 1 over n equal to 0? Well, of course it is, right? We're going to get an infinitely large denominator, and that's going to make this whole fraction go to 0. Okay, so since the limit is equal to 0 and it's decreasing, we know that the series is convergent by the alternating series test. Why write it twice when it's already up there? Alright, so that is going to do it for this video.
So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for sequence